Electric field is defined as an altered region of space where forces would be applied to charges placed in that space. This was an idea that was developed in the mid-1800s to deal with the gravitational forces, magnetic forces, and electric forces that seem to be applying forces from object to object a significant distance away, and they couldn't explain it at the time with the given information they had. So they came up with the idea that the whole fabric of space must be being changed as a result of the presence of a mass, a magnet, or a charge. And so that's the idea, altered space where forces would be applied. And the equation that we use to define the electric field strength is this one right here. The electric field strength is defined as the force per unit charge, as you can see in the top equation in the box. The force per unit charge, force divided by the charge at that particular location, to give you units of newtons per coulomb. So that equation is the definition equation for it. We often use this equation also. This is the equation for point charges. So if you have a single point charge like a proton, electron, a positive 6 microcoulomb charge, anything like that, and you want to find the electric field strength a certain distance of 10 centimeters or 5 millimeters or 2 meters away from a given charge, you would use that equation right there to find the electric field strength in newtons per coulomb a particular distance away from a point charge. Since electric field is also a vector, we determine and sketch the direction of electric fields by placing imaginary positive test charges in this region of space, which is altered because of the presence of this other original large charge. We place small imaginary, these are things that we use just to help us deal with things, small imaginary, positive because of Benjamin Franklin, we just stick with positive throughout all of these ideas about for electrostatics and circuits and electricity and magnetism. Use a small imaginary positive test charge, and the net force on that positive test charge would be the direction of the field. So here's some examples up on the board that you see. The positive charge right here in the middle. This little positive charge right here in the middle. If you place imaginary positive test charges anywhere in the region of space around that large positive charge, the direction of net force on those positive charges would be away, in all directions radially outward from that positive charge. If you have a negative charge down here, this negative charge has, if you place positive charges in the whole region of space around it, they would be pulled inward. So the direction of the altered space, the direction of the electric field is going to be toward the center, radially inward. And if you compare these two right here, these two charges, this one seems to be a larger charge if they're drawn to the same scale because it has more electric field lines in the same region of space. So a larger concentration of field lines generally means that there is a larger field strength. This one over here, this is a combination of two positive charge and a negative charge, and it's the conglomeration of the electric field around the two. And if you place any positive test charges in this region of space, you will find that this is the drawing that you get. And at any particular point in that space, such as right there, the net force would be tangent. Net force tangent to any of these particular lines. So the net force on any curve at a particular point in that space would be tangent to that line. And this, we see this one, this is a positive and a positive. Negative and the negative is exactly the same except the arrows are in the opposite direction. And you see this asymptotic line right down the middle. That asymptotic line right down the middle represents the idea that, well, these lines don't cross. The net force on the left-hand side would be more toward the top, and the net force on the right-hand side would be more toward the top in these center areas right here. But that's what that one looks like. And then a more important one, or a really important one that we use, and that Millikan used in his oil drop experiment when he took those two plates and made them parallel to each other. You take two plates, like my two hands right here, make one positive and one negative charge. In this case, the positive charge is on one side, the negative charge is on the other. Place a whole bunch of imaginary positive test charges in the middle right there, and the force on those positive test charges would be to the right. Those forces are to the right. That means we draw the electric field to the right, and then you have the non-uniform sections over here. So this is very useful. A capacitor with two charged plates that are closely spaced together is very useful for developing a uniform electric field. So it can be very similar to our gravitational field that we have around us, which has a strength of 9.8 newtons per coulomb, 9.8 newtons per kilogram, and is a very consistent uniform field in small regions of space that we deal with. So again, this is the electric field concept, electric field strength, and sketching electric fields.